Sorry, my husband just made dinner or something.
Oh no, you're fine. I just made dinner as well, so I have mine downstairs because I didn't feel like bringing it upstairs.
Oh, sorry, you are. All right.
Hello.
Have you done part 2?
Yep.
Oh man. Okay. I haven't.
It's
Alright.
pretty fast.
It's pretty what?
It's pretty fast.
I just didn't understand it.
All right, let's work on part 2, or at least
Okay, so I did number 7.
Okay.
E because we have to do that too. Did you guys do number 7?
Yeah.
Okay,
Yep.
what does it mean?
Mine was 42,440.
Oh, so yours was way to the left. Mine was 44,560. Sam, did you do it?
Yeah. So I got 4,500, which is like
4,500 or 45,000?
45,000. Sorry.
So yours was the highest. Okay, well, I'm not going to write anything down for that question.
That's fine.
Just what do you notice when we talked about it? Okay, so number 8.
Okay.
Renee, how did you do this one?
Number 8.
Yeah, did you use that, graphing thingy?
Not for the first part. The first part is just asking you what the shape of the distribution will be. Bless you. And because the shape of what they like your parent population, it says it's a normally distributed. So you automatically know that the shape of the sample is also going to be normal.
Okay.
Where it says the normally distributed with the mean of whatever.
Yeah.
Yeah. So anytime it's normally distributed, the sample shape is going to be normal also.
Okay. So how do you know it has the shape?
And that's the answer to B also. How do you know that the distribution of the sample mean has this shape? Because it has normally distributed parent population.
Okay. So what does the mean? Oh, it tells us it's 539.
Yep. So also because it's normally distributed, the mean is the same as whatever the parent population is.
Okay. And then what is the standard deviation?
So the formula for that one is the
Standard deviation.
standard deviation of the sample population. So it's that sigma with the x, you know, like a 0 with an x.
Yeah.
Okay.
Equal to standard deviation, which is 113,
Yeah.
divided by the square root of the number in the random sample. So for this instance, it was 10. So 113 divided by the square root of 10.
Okay. Well, it's not too bad then.
No, it's not too bad.
Does that make sense?
Yeah.
Yeah, I got that now. Okay, so quiz.
Yeah. Are
Yeah.
you ready?
Yeah, I'm good.
Okay.
I just have to find it.
Yeah, I'm not there yet either. We're taping, right?
Yeah.
We have
Yeah, it's working this time.
okay, good job.
Wait, and make sure you post it because he's looking at him this week. I don't know if you read that announcement thing or not.
Wait, what?
He in the under week 3 announcements, it talked about how he's gonna look at the videos. So make sure you post them because he's grading them.
Okay.
Right.
Yeah.
With everyone's name.
Yeah, make sure you put our names on it.
Okay, sounds good. I can do that.
Okay, quiz. True, true.
Excuse me.
Number 3.
Let me open it and
Oh, okay.
okay.
That doesn't make sense. When using the when taking samples of,
And
5, what is the shape of the distribution of means histogram when the parent population is right skewed?
so skewed right.
I think it's
Because it's such a small sample.
yeah.
But then when you go to number 4, when taking samples of 100, the shape of the distribution of means histogram is going to come back to normal because it's the law of large numbers or something, whatever that is.
Yeah, he talked about that in one of the videos.
Yep. Or no, it's not the law of large numbers, it's the other one, the central limit theorem. As the sample size increases and becomes large, the distribution of sample means becomes approximately normal.
So 4 is normal.
Yep.
Okay. Number 5 is normal too, right?
Yep, because the parent
Yep.
population is normal.
Okay. Same with 6.
Yeah. That's like
Yeah.
almost the same question.
Okay, so number 7. I think it's the first, the second, and the last.
That's what I think too.
Mm,
Not the other ones, right? Because that's just, I mean, the same thing. So.
Yep. Because there are 2 ways. It's if you have a large sample size or if it's the parent population is normally distributed. So 1, 2, and 4.
Okay. Um.
If the sample size is large, the shape of the sampling distribution of the sample mean will be approximately normal.
Yeah, that's it.
Last one?
The last one.
Yeah, that's what it is. Okay. Wait, I don't understand number 9. Do you guys understand number 9?
It doesn't tell us really how the parent population is distributed. So are we left to determine whether 36 is a large sample?
Is the question asking for number answer?
I think it is asking for a number.
But I don't know how to figure that out.
Well, okay. Is it going to be the same? Is it going to be 10?
That's what I'm thinking, but I don't.
Because remember on the little applet, like, it had, 25 was the largest sample size that they had on there. Well, I mean, except then, it showed you up to thousands or whatever. So do we determine that 36 then is larger than that? So, because number 10 is then asking you to figure out what the standard deviation is. That's where you're going to do the math.
I have no idea.
Let's see. The sampling distribution of the sample mean is the set of all possible values of x that could occur. You have seen several examples of sampling distributions as you have plotted many means in the simulations and observed the approximately normal distribution that occurs. In the real world, you only observe your sample mean. You do not get to view the distribution. However, the fact that you sample randomly means that you could easily have drawn a different sample and had a different sample mean. There are many possible sample means. You can think about your sample mean as a sample of size 1 from the distribution of all the possible sample means that could have occurred.
In English?
No, I'm like, wait a minute.
I think it's 10.
That's enough to figure out anything.
I think it's 10 because then if you skip down to number 11, distribution of the population is large, so bigger than 30, and we're looking at a sample size of 36, the shape is going to be, of the distribution of the sample mean is going to be normal. So that would indicate that the mean of the population and the sample would be the same.
So it's 10?
Yeah.
That's what I
I
think.
don't know how to get a different number from what they gave us. Like,
Yeah, I don't either.
Right. So then we have to do the math on that one, though.
to figure out standard deviation from the 36. That
Yep.
thing?
So it's going to be,
Let's see.
really?
What?
I'm doing math in my head. It's a scary thing.
Hey, can you come close?
Um,
Tell me when you guys are there, because I don't like my answer.
I don't even know how to do it.
All right. This is directly from one of, on the videos, his key points at the very end, which is about word for this question. The standard deviation of the distribution of sample means, which is what we're looking for, equals the standard deviation of the parent population,
Which is
so
6.
6, sorry, divided by the square root of the sample size, which is 36. So the square root of 36 is 6. So it's 6 divided by 6. Right? 1.000? See why I don't like it?
On our last thing, the standard deviation was all like decimals, but on this one it says the population standard deviation is 6.
Yeah.
So I mean, it kind of makes sense just to be 1. That 3 decimal places could just be there, like, because it's on all of them. I don't know.
yeah, I have no idea.
I'm going to put it.
Yeah, I'm just putting 1 because I don't know.
I'm going to do 0.000 though. I don't know if it'll change it or not, but.
Yeah. Okay, regardless of the distribution of the population, if the sample size is large, so bigger than 30, what would be the shape of the distribution of the sample mean?
So,
All right, I turned mine in. 1 is right. 1.000 is what I put.
Wait, what did you do for the last 2?
Well, number 11 is using that rule that if the sample size is large,
then it's
the
normal.
distribution shape is always going to come back to approximately normal.
So is it law of large numbers or central limit theorem?
Isn't it central limit theorem?
Yep, it's central limit.
Okay.
The law of large numbers is just talking about that when you start, the bigger your sample size is, it speaks more to accuracy. Like you're going to get a more accurate, it draws closer to the population mean.
Okay.
But central limit talks about the shape.
So is everything else right?
Yep.
Yeah, it should be.
Wait, you put 1.000, right?
Yep.
Yeah.
Sweet.
Okay, cool.
That only took us 20 minutes. That was good.
Yes.
Okay.
All right, well, thanks, guys. I will see you on Wednesday.
All right, and you're going to
I'll
post that.
post this, yeah, and I'll add everyone's names onto it.
Awesome. Thank you. See you guys on Wednesday.
Okay, see ya. Bye.
Bye.